All right, our group project is working on a pilot plant in Springville that's purpose is to manufacture water-soluble films. What we're doing for our project is we are controlling an actuated valve that feeds water to a mixing tank, and we're controlling that using a level sensor. Our goal with this project was to fill a tank with 100 gallons at a max flow rate of 4 gallons per minute. We didn't want any overshoot because this is based on a chemical recipe, and we didn't want to add too much water to influence the quality of the solution that we're creating. We wanted the system to remain inactive while we were mixing the water with powder and also while the tank was emptying, and we wanted it to begin filling when it was completely empty.
For our PFD, we did a parallel system where there are two tanks. Starting from the far left, we have two level controllers, which control the water feed into the tanks. And then we have a level transmitter, which measures the height of the water. And then lastly, we have our feed controllers, or our feed controller, which controls the valve at the exit. And ultimately, we let one tank fill, and then the PID becomes inactive, which gives enough time for the second tank to fill. So the logic portion of our controller is essentially allowing one tank to fill while the other one mixes for a set amount of time. And that assures us that the solution has reached steady state in mixing. And then once that time period has expired, then we do open those valves and allow the full tank to empty. And then during that time, while it's emptying, the other tank is filling. And this is all being controlled by that level transmitter and controller.
In order to accomplish this, we decided to build a simulation for the tanks because we're still in the process of purchasing our equipment. To do so, we used a material balance for the water going in and out of our tanks, as well as adding powder at a certain point halfway of filling the tanks. We used this material balance model to create a simulated data set, which we ran step test with so that we could fit a model to it. We chose to start by using an FOPDT model and ran a regression to find values for the Kp, Tau p, and Theta p parameters. This resulted in this fit that you can see here. Unfortunately, when we had our valve go to 0, the FOPDT model was unable to keep a 0 slope, but instead wanted to decrease the amount of liquid inside of the tank. We think this is because the FOPDT model is built more for systems in which it's able to adjust to a set point by adding to and taking away from a system, whereas for our system we just needed to fill to a set point without being able to decrease.
In our experiment, we model our system using a physics-based model as discussed by Chandler. The materials balance was sufficient for modeling our system accurately. We used the Kc value found in the FOPDT model to model our P controller. Ultimately, we set up a logical P-controlled system. The logic portion of the controller allowed us to fill one tank while the second tank empties. It also allows us to add a delay time to achieve complete mixing. Ultimately, we only needed the P portion of the controller because it was an integrating system.
Here you can see the control system for both tanks superimposed on each other. From this, you can see that at all times, a tank is either emptying, mixing, or filling. This allows us to achieve steady state while operating CSTRs that require an extended mixing time. The next steps for this project are to buy the necessary equipment needed to test our physics-based model. We plan to use the same controller for the entire plant, which would include around 25 inputs and outputs. We expect that we'll need a distributed control system for the plant. We plan on buying a Micrologix 1400 for this job.